Hello everybody. Hope you all are enjoying yourself and welcome to Introduction to Computer Organization and Design. Well, moving on. My name is Rajat Bhattacharya and I'm passionate about teaching, quizzing, computer hardware and public speaking. Currently I'm pursuing a BTech in Electronics and Communication Engineering from Indian Institute of Information Technology, Guwahati. Moving on. Some prerequisites for this course: some basic programming knowledge, let it be C or C++ or Java. Then we need some knowledge on digital design, stating of which I mean to say adders, subtractors, multiplexers, finite state machines, and of course Boolean logic. So, what to expect from this course? Well, you have tuned in for this course for some motive, and I'll be telling you what you should expect from this course. First, you should remember what I tell you in this course. Secondly, you should understand each and every part that I talk about in this course. Thirdly, you should know how to apply your understanding into the components which I teach in this course. Then you need to analyze those components. After analyzing, you need to evaluate and create so as to pave a way for new innovations. Moving on. Welcome. Welcome to the art of hardware design. Welcome to the art of abstractions. And welcome to the path of the world of systems. First, we are talking about computer organization and design here. So you need to know about hardware, because this is all about hardware that we will be talking about. Next, we need to know about the art of abstraction. Abstraction, we are minimizing the lesser details and we are focusing on a particular stuff as a whole. We'll get back to abstractions in a broader detail. Moving on to the world of systems. What do we have next? Well, let's have a pervasive idea about abstraction. Abstraction, it is the only way of dealing with complex systems. Well, I have considered a real life example here. Let us consider a man who is driving a car, and let us consider he does not have any knowledge about the internal functionality of that car that he is driving. So basically, he just knows that he is pressing the accelerator, the car is moving in a certain direction, and when he applies brakes to it, then the car stops moving. He does not know how applying the brakes would influence the car's mechanical property so as to stop the car. Hence, this is what abstraction is. You might be thinking that, yeah, being engineers, we need to know about each and everything, each and every detail and each and every part. It should be fixed, like it's like a jigsaw puzzle. You should know each and everything about it. But certain cases should be exempted from that ideology, as going on and on like that will create problems in the future, and you definitely do not want to face problems. Next, we have layering. Well, abstraction discipline makes life even simpler. Well, that's what I was talking about. Going on and on, layers by layers. You have a thing of n levels, you go by the n minus 1th level, n minus 2th level, and so on and on. But sometimes it's better to keep it that way. Let's go up to n minus 1th level, maybe, at most. But we do not want to go any further, because that will add to more complexity, and we definitely do not want complexity. So, what is a computer? Well, you might be thinking and laughing about it, that what I've stated in this slide, that you might be watching this video on your mobile phone or maybe on your laptops or desktops. You will be using mouse, keyboard, and all that stuff, and I'll be thinking, yeah, I know about it. But yeah, that is a point that why I have stated this slide up here. So, talking about the components of the computer, we have some input components like the mouse, keyboard, and stuff. We have output components like display, printer, speakers. We have the memory like caches, DRAM, SRAM, hard disk drives, flash drives. We have network. Speaking of networks, we have these wires and stuff, both input and output. Then what our primary focus in this course will be is the processor. See, the processor is implemented using billions of transistors, and it is not possible for us to study each and every transistor, is it? It is not, right? So we will study about the data path and control, and as it is impossible to look at each and every transistor on a on a chip, so that is why we need abstractions for it. That is why I was constantly stressing on the fact of abstractions. Abstraction is the way you do a course on computer organization. Well, that's what my teacher said, and that's what I'll be telling you. Now, moving on, what do we have? So, what makes a computer work? Well, you might be thinking, yeah, what makes a computer work? How is it related to this thing? Yeah, but it's pretty much well related. Well, we have these things like application software, system software, then we are going to the assembly language, then machine language. Like we are going level by level. The layering thing that I talked about earlier, that you have something of n levels, then you are going like n minus 1th level, n minus 2th level, and so on. So in the end, in the slide you can see you are ending up at CMOS technology, then semiconductors, silicon used to build transistors, and properties of atoms, electrons, and quantum dynamics. And you'll be stressing on like you might be thinking that you are going towards the origin of life and all that thing, the presence of matter, who am I, and all that. Yeah. So in the end, these things make a computer work, but we need abstractions to deal with it. And what is the most important thing in this world? That is sellability of a product. It's not creating a product, it's the sellability of that product. You might create a very very good thing, and you might be thinking, right, I've done so good in this aspect, and this thing works really well, but does it sell? In the end, that counts, the sellability of that thing. Speaking of sellability, moving on to some different aspect. So what I stated earlier is described here in a diagrammatic fashion. This is what software is, and this is what hardware is. In the lower part is the hardware, in the upper part is the software, and in the middle you can see a purple line and a purple writing written as ISA. So what is ISA? ISA is instruction set architecture. You should definitely remember that ISA is the point where the software meets the hardware. ISA is that point where the software meets the hardware, because our whole course will converge into ISA in the end, and it's really important that we know about ISA. So moving on, what do we have next? The thing that I talked about earlier, right? So what did I talk about earlier? This computer architecture thing. So speaking of which, you have this blue line out here, then you have this hardware stuff comprising of memory, processor, input output system, data path and control, and so on and so forth. Then software stuff, that applications, OS, then compiler, assemblers, and stuff like that. And this blue line is the instruction set architecture that I was talking about. Speaking of which, we move on. So this diagram precisely describes about the ISA. It's a funny diagram, I'll say. You have this hardware thing, hardware guy standing tall like a bodybuilder, holding the instruction set, using his whole muscles and stuff, and the software people just dancing all around the instruction set. That's what it means. You are just the hardware is fixed, right? You are not changing the hardware, but you are making different implementations on software at your current level, right? You are writing programs for that, but you are not changing the hardware. This is what this diagram describes. Speaking of which, we can move on to the next slide. Well, this instruction set architecture. So we should note that the instruction set architecture is an abstract model of a computer. It is also referred to as architecture or just computer architecture. A realization of an ISA is called an implementation, and an ISA permits multiple implementations that may vary in performance, physical size, and monetary cost. Because the ISA serves as the interface between the software and the hardware, as a border. One more important point one must note is that software that has been written for an ISA can run on different implementations of the same ISA. This major thing has enabled binary compatibility between different generations of computers to be easily achieved and the development of computer families. Both these developments have helped to lower the cost of computers and to increase their applicability. Right in the end, we are going to the fact of sellability. How can we sell a product we create? So, for these reasons that I've stated earlier, the ISA is one of the most important abstractions in computing today. ISA and abstractions go hand in hand, right? And the yeah, a major question that is generally asked is where is the ISA implemented and where is it realized? Well, people should know that ISA is implemented in the software and realized in the hardware. This is a really important point that everyone must note, right? And an ISA defines everything a machine language programmer needs to know in order to program a computer. That's what I was talking about. So I talked about the advantages of ISA. Talking of its disadvantages, well, it sometimes prevents using new innovations. Look, coders are generally lazy people, right? We do not like to write a code again and again. We just fix to one code, and at most we will try to do what? We'll try to optimize that code, right? Because a code for an ISA will last up to hundreds and thousands of lines, which you know a coder does not want to do, right? Because if somebody has put enough research onto it, a coder will say, yeah, they have done a good job. Now if it's working well on it, well, let's move on with it. No problem with that. Okay. So that is why sometimes it's preventing new innovations, but nevertheless, it's on a minimum scale. Well, speaking of some common ISAs, which you must know, are the IA32, then IA64 is there, then you have this PowerPC, then MIPS, which we'll be talking about in this course, is MIPS. Then you have the Spark, then ARM. ARM, you must be knowing about ARM, as maximum mobile phones that we are using consist of ARM ISAs. Then you also have this x86 architecture of Intel. Well, let's share a fact. Well, people say that Microsoft made a lot of money due to Intel, and I believe the same, because this x86 architecture was so beautiful for this Windows platform to run on it that Bill Gates could use it to sell it on a larger and broader scale. That's why most of us are using Windows on a day-to-day basis. Of course, many of us are also using Linux distributions, but nevertheless, these are the things that we must talk about. Moving on to the next slide. This case study. Okay, so in this course, we are going to study about the MIPS ISA because we need to know about the data path and control that I've talked about earlier, right? And the performance of different things, how can we optimize things. So we need a sample for it, so we'll be studying MIPS here. So there are here I have listed some instruction categories of MIPS. We'll do these in a broader aspect further. Then some categories like load and store, computational branches, and jumps, floating point operations, memory management, special categories like, and in the right side I have described about some I type, J type and R type instructions. Well, we'll talk about them definitely so as to solve some problems about it. And that's what it is for the introduction part for computer organization and design. Well, hope you like this introduction, and thanks. Do tune in for more. That's it.